The joint webinar between Anritsu and Amatech. Hope everyone is doing well and staying safe. My name is Mohan Puntambekar, and I'm a field applications engineer at Anritsu. Now, today the topic of my discussion is differential measurements using Anritsu VNAs. And initially, I'll just begin with speaking about single-ended versus differential signaling, followed by what kind of noise immunity you get when you do differential signaling. We'll then talk about common mode rejection as well as differential measurements, and then go over the common mode and differential setups. Then we will speak about how Anritsu VNAs carry out differential as well as common mode measurements. And we will then speak about using VNAs for signal integrity measurements. And then the last two topics would be superposition versus true balance techniques that we use when making these type of measurements with the Anritsu VNAs. And finally end with a brief discussion about how to carry out crosstalk measurements. So just wanted to begin with going over some single-ended versus differential signaling, what it means, and so forth. So single-ended is basically unbalanced devices which have all of its signals referenced to a common ground potential. Now, when you look at a balanced device, by comparison, it's composed of two identical halves. In balanced signaling, you have two conductors with an optional shield. Shield is obviously recommended, and they're transmitting the same signal at opposite polarities and have equal impedance to ground. Now, if you operate a balanced circuit in a common mode, it has no performance advantages over a single-ended circuit. The advantages of the balanced topology come from operating the device in a differential mode. Now, when the device is driven differentially, you have a virtual ground that is established along its axis of symmetry. And if the transmitted signal is the same polarity, the circuit is actually considered operating in common mode. And if a device has both conductors operating in differential or common mode, then you're set to be operating in the mixed mode. And I always like to think in terms of pictures. The pictures at the bottom, they speak 1,000 words. The first picture on the left is you have two signals with opposite polarities going into the device under test and coming out differential, meaning opposite polarities also. And the second one is common mode, where the two input signals are in phase. And then you have a mixed mode also, when you go in differentially and come out single-ended. Just wanted to go over the benefits of using a differential system. And again, as I said, picture speaks 1,000 words. What you can see from here is it takes twice as much as noise to cause an error with a differential system as compared to a single-ended system at the top. And this is more illustrated in the next slide. You can see here that you have some noise here on the single-ended receiver, and you have noise on the differential, each arm of the circuit. And you can see that in terms of the noise immunity at the end of the single-ended receiver, you have Vs minus V noise. And when I say the noise immunity is doubled, you can see it's 2 Vs minus V noise on the differential system. That's why the noise immunity has actually doubled. Moving on, common mode rejection basically is the rejection by the differential device of the unwanted input signals common to both inputs. In other words, you can see how the common mode noise is actually rejected by using differential signaling. And as I said, this example, there is unwanted noise that is present on both inputs of this receiver. But because the output is the difference of the positive input and the negative input, the noise is effectively rejected by the differential receiver. So that's one of the primary advantages of differential signaling. So just wanted to go over differential measurements here. Now, whenever there is an imbalance in a differential system, the fields no longer completely cancel each other. And what you have is a resultant current is called a common mode current, which is what causes crosstalk. Now, differential VNA measurements can either be acquired using a 4-port VNA, which has 2 differential pairs, or with a 4-port VNA that uses 4 single-ended measurements, which is what we refer to as the superposition theorem, which is applied to calculated differential measurements. You have a total of 16 parameters that are required to describe the various combinations of differential and common mode signals. And these may be used to characterize a differential path single-ended VNA measurements, which could be taken using the VNA, and then you can calculate to determine the differential characteristics. This picture here just illustrates the various scenarios. The first one, you have 2 common mode signals going in, common mode signals coming out, which are both in phase. Now, the second picture is common mode going in, differential out. Differential meaning they are 180 degrees out of phase. Then third one is differential in and common out. And the last one is differential in and differential out. So just wanted to illustrate this in a pictorial manner. And again, in summary, common mode signals are 2 signals with a phase difference of 0 degrees, as you can see here from the first plot here. And differential mode signaling is where the 2 signals are 180 degrees out of phase, like shown in the second picture. This just illustrates the differential S parameter graphic, the 16 parameters that we spoke about earlier on. And these are the ones that are or can be measured using the VNA. And I'll talk about this in quite a bit of detail on the following couple of slides. So what I actually have here is I've described every signal, every measurement combination that is possible and in which direction that can happen. So now let's talk about this picture. You have a device under test over here, which has differential input, differential output. Ports 1 and 3 form a logical or a balanced port 1, and ports 2 and 4 form the balanced port 2. So going in this direction, you have SC1, C1, D1, D1, C1, D1, and SD1, C1. That's at the input of the device. Now I've described exactly what these signals mean. So let's take a couple of examples. C1, C1, as you can see here, is it's injected at port 1 and measured at port 1 also. And what does that mean? It means you inject common mode signals into port 1 and measure the reflected common mode signals at port 1 itself. So basically, it's like a common mode S11. And that's what I've mentioned here in the comments. Now, by the same token, what does SD1, C1 mean, for instance? So that is when you actually inject common mode signals into port 1 and measure the reflected differential signals at port 1 itself. And that's called the mixed mode S11. And then you can, in this forward direction here, you can measure SD2, D1, for example. Now, D2, D1 is when you inject differential signals into port 1 and measure differential signals at port 2. So basically what we're trying to show here is all the possible measurements that could be carried out using the vector star VNA. And the table below actually describes each and every one of them and the directions and what they all mean. Now, the next slide is going to be describing a mixed mode scenario where you have a balanced pair at the input and a singleton, as we call it, at the output. So here we can inject differential or common mode signals at the input, and you can measure signals at the output. And the table at the bottom, again, like the previous table, describes what type of measurements are possible And what do they mean? So if, for example, if you have SDD, SDD is basically you inject differential signals into port 1 and measure the reflected differential signals at port 1 itself. And then if you wanted to measure the differential and single-ended forward gain, that's SXD, the second measurement in the table, which means you inject differential signals into port 1 and measure the single-ended signal at port 2. And on our VNA, you have this nice GUI, which represents exactly how the signals are hooked up. And I think, again, picture speaks 1,000 words, so it's very useful to have this sort of a pictorial representation. So again, these arrows represent the various directions the signals travel in and what kind of measurements are possible in that particular direction. Moving on, we are going to be talking about signal integrity measurements using VNAs. So VNAs are basically very useful in determining the actual cause of a signal integrity problem. They are excellent tools for understanding, for instance, what is causing an eye closure. By the eye, I mean the eye diagram in high data rate systems. So these pictures here just illustrate how we hook up our VNAs to various signal integrity applications. So as I mentioned before, VNAs are actually helpful in understanding physical structures and their imperfections. If you have printed wiring boards, because no manufacturing process is perfect, so you wanted to actually verify using measurements by VNA of real-world channel defects, things like tolerances on PCB artwork, plating, dielectric thickness variations, and so forth. Now you can also use VNAs to evaluate connector performance, how well they're actually mounted on the PWB. Or you can use the VNAs to analyze multi-layer PCB stackups. And again, VNAs could also be used to correlate measurements with the engineer simulations to measure results. Now, a lot of design engineers using EDA tools to simulate the channel before they actually go ahead and build it. So this way, you can improve your speed of the time for market to design. So now we're going to be speaking briefly about superposition versus true balance techniques. Now, as I mentioned before, the superposition technique is when you have one single source and you actually mathematically derive the differential and common mode transmission line characteristics through superposition while stimulating just one side of the balanced transmission line one at a time. In the true balance technique, you use two sources to create the actual differential and common mode stimuli. And that's why we term it as true balanced. So for the most complete description of balanced devices, you have the mixed mode S parameters, and you have 4 blocks of 4 parameters: differential parameters, common to differential mode parameters, differential to common mode parameters, and only common mode parameters. And these are the 16 parameters that we spoke about earlier on. And you can see that in the picture on the right. So now concentrating on the superposition technique that I mentioned earlier on, you can see there's a single source here, which is obtaining single-ended measurements. And then what the algorithm inside the VNA does is the mixed mode parameters, and by that I mean the differential and common mode parameters, are mathematically derived from the standard 4 S parameters of the device. Now, the advantage of this method is that you only need a single source and not a dual source as required in the true mode method. And the true balanced mode is where you require a dual source, and that directly measures the differential and common mode parameters, unlike the superposition technique, which uses single-ended parameters. So these two sources are phase coherent, and this technique uses active phase and amplitude control of each of the two input sources. Now you need very precise calibration for this sort of technique. And the reason being, you're controlling multiple sources with precise magnitude and phase alignment. And that can potentially limit the stability of the calibration over time. So basically, as I said, the true balance technique uses a dual source VNA with the sources that are synchronized with a 180 degrees phase difference. And you can measure the common mode and differential as well as mixed mode parameters directly. So which technique is better, superposition or truly balanced technique? Well, it depends on what you're trying to measure. So most signal integrity measurements, such as passive components and transmission lines, you can use the superposition technique. And even active devices, provided they are kept in their linear region. So for instance, if you're measuring an amplifier, as far as it's in its linear region, you can use the superposition technique. So if you have active devices that are driven into compression or saturation, then we recommend that you use the true balance technique. And again, the table on the right has some recommendations on which technique to use for a given application. And then these are basically the trade-offs between the superposition as well as the truly balanced technique. So as I mentioned earlier, you have to make sure what type of device under test you're using. If you're using something which is under compression or saturation, we recommend that you use the true balance technique. And for passive devices, such as transmission lines, you can use the superposition technique. The superposition technique, as we spoke earlier, the method of obtaining differential parameters is calculated, whereas the true mode technique, you're measuring these directly. Now, I just wanted to briefly mention why to use the true mode technique when you use devices that are under compression or saturation. It is because the input VSWR, or the return loss of the device, is constantly changing. Therefore, to keep track of that, you need sources that are phase coherent. That's why it is best to use the true balance technique for those type of applications. Again, the overall solution cost is true balance technique is slightly more expensive as compared to the superposition, because you have two sources as well as a combiner in the VNA, and the superposition technique just uses a single source. So again, it really depends on your particular application. We'll just end by briefly going over crosstalk. So you get crosstalk, which is an undesired coupling that occurs as a consequence of microstrip traces or unshielded dual conductor cables in close proximity to each other. So this is mainly due to capacitive and inductive coupling along the lines. So you have two different types of crosstalk. One is the next, which is near-end crosstalk, and that happens when the signal from a transmitter at one end of a cable interferes with a receiver at the same end of the cable. Now, the other one is fixed or far-end crosstalk, and you get that when a signal interferes with the receiver at the opposite end of the cable from the transmitter. And you can see that illustrated in this picture here of how a device would be hooked up when you're measuring next in the scenario on the left, near-end crosstalk, and the far-end crosstalk is being measured in the second picture. Now, I'll show you some more pictures which will illustrate this even in a better manner in the next slide. So let's say you have these twisted cable pairs in RJ45 cables, and for the next, which is the Nearend Crosstalk, this you are injecting a signal on this blue cable here, and you are measuring the crosstalk itself on this end here of the other twisted pair. Whereas on the fixed, let's say you're generating the signal over here. Now, instead of measuring it here, you're actually measuring it at the far end. And that's why the term far end crosstalk. And finally, the crosstalk is generally specified as a percentage of the signal that appears on the relative victim line relative to the aggressor line. Now, it is normally expressed in dBs. And what users do, they usually create a limit line in accordance with their specs and then make the measurements. So what you see on the picture on the right is you could measure the NEXT as well as the FEXT for a differential channel in a two-channel differential system. So you have three traces over there. You're measuring the insertion loss as well as the next and fixed crosstalks. Very useful. Okay, and that's all I have. So if you have any questions, please feel free to reach out to me on the email that I've shown on your screen. And with that, I would like to pass over to Chris Gibson of Amatech.
Okay, what I'd like to talk about is one of the things that I think a lot of people tend to overlook is, what are we going to do if we're going to try to automate our switching in a microwave environment? And a couple things I'd like to do is let's start off with some basic terms here. First thing is we talk about what is called an RFIU, and just as a quick definition, the RFIU is kind of the glue that connects up our instrumentation, if you will, to our device we want to test. And again, this could include anything from your spectrum analyzers, your VNAs, synthesizers, power meters, to whatever it is that we're going to be testing, whether it's a black box or a circuit board or whatever. And again, a lot of times when we talk about an RFIU or switching in general, this is really what allows us to automate our testing. And again, it could be much more than switching. It could be combining, splitting, filtering, amplifying, any of those things that we need to do to be able to take our signals and put them into the proper framework so that we can switch that into our device under test and make our measurements. So when we typically think about, what are some of the challenges with an RFIU development, what you see on the left is kind of typically what we're faced with. We have a general block diagram or schematic that says, this is what we need to do, and we need to turn that into some type of an instrument that we can actually use, support, and do all the things that we need to do our testing. So we're going to talk a little bit about some of the challenges and some of the options and things that we have in front of us. So when we look at the real costs of, say, we want to develop a custom RFIU in-house, a lot of times these things can become a project within a project. And what we mean by that is it requires a lot of different multiple engineering disciplines or resources. We need our RF engineers to do the design and the checkout, the electrical guys to take care of all the control side of it, mechanical guys for the box design or the cooling, and then of course software guys are going to be responsible for putting together some type of a driver or the ability to communicate with the switch system. And again, when we look at these project within a project type situations, there's the potential for schedule slip. We know that sometimes some of these in-house designs tend to be poorly documented, and so there's a lot of reliance on tribal knowledge. And again, these, although on the surface it may appear to be cheaper, sometimes these added costs can actually get in the way and vastly exceed what we expect to pay in our budgets that we have outlined. So we'll talk a little bit about some of the options that we have in front of us. So how's the best way to address this? So obviously, developing in-house is one way to do it and continue to use all the available resources that we have. The other way is to look at a modular off-the-shelf switching solution. So here's some examples that I've got up here. VTI, we actually work in a number of different platforms, but we've got customers in the VXI or LXI or PXI platforms, and they all work fine. But again, here in a modular approach, you have the ability to buy various modules and put them into a chassis, and there you go. You can easily create a very commercial switch solution that way. The third option would be working with an integrator and design a custom RFIU. And these are just some examples of maybe some custom RFIUs. And we may talk a little bit about some of the specifics of these and what makes these maybe advantageous. So looking at this, let's kind of compare some of the advantages and disadvantages of going with, say, a modular approach versus a custom approach. The nice thing about a modular approach is it works in a lot of our standard environments, like we kind of mentioned, VXI or PXI or LXI. So it works in that environment if that's where we're already at. A custom RFIU, those are designed very specifically per a customer's requirements. So when we look at a modular RFIU, it tends to be lower in cost because you're just buying off-the-shelf pieces and assembling it. With custom RFIUs, the cost is more because you've got some engineering involved, but you can do things and techniques to manage it by using standard building blocks to minimize any custom engineering that you might have to do. So that's one approach. When you go back to a modular approach, you can very easily configure them by just changing or replacing some of the relay modules. So if you have a situation where testing changes and you need to, you're using maybe a 1x6 combination with something else, you just change out the modules and it's very easy to do. The downside with a custom RFIU is it's very specific and it's designed to work in one very specific application. Back to the modular approach, though, you've got that flexibility, but again, all of your cabling is going to be located on the front or external to the box. So you've got the cabling that's hanging out, and in some situations, depending on somebody could brush up against the cabling and you could get a change in performance and stuff, and so you may have to look at that. And whether you're in an R&D environment or a production environment, that may be very important to you. The nice thing about a custom approach is that all of the cabling and all of that is enclosed within a box, if you will. So there's no real external wiring. You basically bring in your inputs and your outputs right through the ports on the box itself. So that is one of the advantages of a custom RFIU. Back to a modular RFIU, we're generally limited to relays and maybe some basic microwave components. Again, it's a very modular approach to it, but when we look at a custom RFIU, we have the ability to incorporate a wide range of components, everything from relays to amplifiers. We can bring in splitters, combiners, attenuators, anything that we need to do to modify that signal. And so that again is one of the advantages of a custom RFIU. So if we do decide that a custom RFIU is the right way to go, what are some of the things to look for in a quality design? Obviously, we need to make sure that we've got full documentation. We need to be able to support this for the lifetime of whatever it is we're going to be testing. And maybe if we're in a production situation, we may want to duplicate that so we have identical RFIUs. So documentation becomes very important. Because it is going to be in an environment we want to control, we care about the digital communications. How easy is it for us to integrate this into our, say, test protocol or test software? If we're going to automate it, we have to be able to control the RFIU and get it to function the way we need it to. We may need to design it for maintenance if it's going to be something that's going to be used for the long haul, particularly if it's in a production environment. Sometimes we need to have more of a COTS approach, especially even if we need custom requirements. And one of the techniques that can be done is, what if we pre-design it by using 3D modeling? You know, if we do that, we have a better idea of what we're going to be able to expect. And one of the things that we've also found is that by 3D modeling it, we have the ability to, if we need to build multiple units, we can design them so that they are clones by following what's done in the 3D model. So we'll kind of go over some of those specific examples. So again, when we look at a good RFIU, we need to make sure that software is where we need it to be to make it easy to control. This is just an example of what we call a soft front panel, you know, and here's one that we use where basically we use Java on the soft front panel, where it's very easy for the user to go in and actually, without having to write any software, he can pull up a browser and he can actually go out and control the switch modules manually just by clicking on the GUI there. So it makes it very easy to kind of test and check out the system. All of this stuff is designed to make it very easy, but the intent is that users can use the product just like they would any other instrument. They don't need to be a software guy to figure out how to be able to close the switches and get it to function the way that they need it to do. Of course, we need to make sure that we document and test every RFIU that we're going to plan on using, and that includes, you know, full system characterization. We want to make sure that we have an acceptance test procedure to make sure that the box is doing what we need. The dirty truth about switching is that ultimately we spend a lot of, you know, we spend a lot of money on the instrumentation that we're going to use for testing. But anytime we pass any of the signals through some type of a switching network or pass through, there is some level of signal degradation. We need to make sure we account for that. But again, let's design for the highest performance that's available, but let's understand what we have. And testing is one way to do that. Of course, we need documentation. We need to make sure that all of our products are fully documented so that it makes them easy to service. It also makes them easy to support in the long haul. And again, one of the techniques that we found is 3D modeling. So on the left, you'll see an example where this is an RFIU where the customer was concerned about bend radiuses of the cables and a number of other things. And by doing a 3D model, we can say, listen, this is what we believe we can do. And on the right, you'll actually see the actual implementation of that design. So 3D modeling works very well. The other thing that it allows us to do, like we were mentioned earlier, was if I need to make a clone, it's very easy because now it's fully documented, and in a production environment, it's not just a handcrafted custom box. It's actually manufactured to be, you know, item number 1 is the same as item number 5 or 10, if you will. So 3D modeling is a tool that we use, and it proves to be very valuable for us. I just have a couple of case studies that I kind of wanted to go through real quickly. One here is for an RF radio manufacturer. They were asking for a 12 by 12 matrix. They wanted to connect up any 12 instruments to any 12 of the radio ports. You can see that it's fairly complex and that there's a lot going on. You've got 200 cables, 200 relay drive lines, and of course, you know, there's a lot going on. But again, this is just a simple matrix, if you will. Here's an actual view of what the product looked like. What you'll see here is that all of these 200 cables are nice and neatly enclosed inside the box. The other side of it is you'll see that we've designed it so that this panel can, if you will, rotate out, so it's easier to support that in the event that we have a relay failure. We can go in and easily, you know, get access to the relays to be able to replace those or replace any faulty cables or anything like that. So here's an example of a fairly large matrix and what you can do from a custom standpoint. If we were to do this with a modular approach, it would be prohibitively large, and also you'd have so many cables it could be difficult to support. Here's another RF matrix. It's a dual 2x16, very high performance. They had some very aggressive insertion loss and VisWire requirements, 26.5 gig system. Here we use some radial relays to be able to do that, but we find that we use relays from a lot of different manufacturers to be able to give us the best performance and the best options as far as delivery and stuff. So again, these are things you need to consider if you're looking at a custom RFIU. Here's another very simple one that was designed for an IoT customer, a very simple 4x4 matrix. They wanted it very easy to use, and they were working in a Python or Linux environment. Here's another example of designing for accessibility or maintenance. We had to put in access panels so that we could get, in there to be able to make any changes or maintenance that might be required. Here's a very large matrix that was designed for a military aerospace customer. It was a large chassis. It was an 18 by 18 matrix with 744 total pass, 40 gigahertz. Very aggressive VisWAR performance was needed. So here's an inside look at the box. You can see how it was laid out to try to minimize bend radiuses in the cabling so that we could get the performance that they were asking for. But again, this was more of an extreme case with a full 18 by 18 matrix. Here's an example of one that we would call a very high performance matrix. It was only 20 gigahertz, but they were asking for phase matched paths. So again, here's a situation where cable lengths were critical, and the design and manufacture of this thing was essential to be able to meet those requirements. But we see this from some of our military aerospace customers, some very demanding requirements. But again, just kind of an overview. We know that most of you, if you're looking at going into automation, you need to think seriously about how you're going to handle your switching or your signal routing. An RFIU approach is, one way to do it. And depending on the requirements, you may decide that a modular approach is the right way to go, and there are a lot of good tools for that. Then it's just a matter of what platform you want to be on, and then obviously the option for custom is there as well. So just kind of wanted to present those options out there, that there's a lot of different ways you can go, but appreciate your time. And you can see here's my contact information. If you have any questions, you can reach out to me, or at this point, I guess I'll turn it over to Tina on the Q&A session here.